Right, so we are going to jump straight into page 14, right? The last 3 pages of content before we talk about a summary. So we have IV graphs for varied frequencies. Okay, here you must read the criteria very, very carefully. We are varying the frequencies, we are varying the wavelengths, right? Because frequency and wavelength is linked by speed equals to f lambda. However, we are assuming a constant arrival of photons. Okay, we are not assuming constant intensity. Can you write that down in contrast? We are assuming constant rate of arrival of photons. Why is this important? Right? Because if you have a constant rate of arrival of photons, you should have a constant rate of emission of electrons. Right? And hence, the current that you measure should be the same for all frequencies when the V is positive. Okay? This current is also called a saturation current. Next, if you have a certain frequency, a certain wavelength, you have a certain potential to stop it. That's a stopping potential. This graph, I want you to compare. I'm showing you this graph. I want you to compare to the graph on page 13. When I vary the wavelength, I am varying the frequencies. So these two graphs should look the same. But I purposely show you a graph that is different. And in fact, the graph that you have and the graph that I have on the screen is also different. These are the little intricacies. I purposely put it in. Okay? Why? Okay? Notice that for me, the one on the screen, the current reaches saturation current at V equals to 0. Notice that. But in yours, the current does not. You need a certain V before it reaches saturation current. Why? Okay, it's because of this concept. It depends on your setup. I draw for you now the emitter, and I draw for you now the collector. Imagine your electrons are moving out in this direction. A range of angles. When your V is 0, will this electron and this electron, it will not be captured by the collector, correct? It is only when this is positive enough that these electrons will then curve towards the collector, which explains your graph. Now, I wouldn't know which graph Cambridge will present to you. I'm not sure how deep they want to know this. They just say, oh, have an understanding of how it works, right? But that's like me telling you, understand how the stock market works, and then ask you a question that you don't even understand, right? Like, how deep can you go, right? So this is one of the possible variations that they can ask you, right? How, in the case in your diagram, why does your current not reach saturation at V equals 0? This is the answer, right? Because the electrons at V equals 0 may not be in a direction towards the collector. So why in my diagram, in my graph over here, why is it fully saturated? It depends on your setup. So let me try to erase this, and I will draw for you a different setup. Eraser. Okay. There's my ugly drawing. What if your collector looks like this? Right? If you want to collect all the electrons, how would you design your collector? I will design my collector. Now, I don't need to care which direction my electron is going out. Agree? Right? So I can collect all my electrons as long as they come out. So you will have a variety of graphs of whether saturation current reaches zero depending on the setup. Okay, I have even seen a collector that looks like this, right? In one of the setups, looks like this. I've seen a collector emitter diagram that looks really strange, but I just want to show you for exposure. The collector was like that, perpendicular to the E. Oh, interesting, right? So these are possible setups that you can do. Okay. I want you to also contrast this diagram that you have with the graph you have, these two graphs on page 13 and 14. What is the difference? You'll notice another difference. In fact, a few of you came and talked to me last lecture. You'll notice that in page 13, the graph looks like this on the other hand. It's an S-shaped curve. Whereas here, it's like a convex curve and that's it. We generally accept both. But allow me to explain why most of the time we see the S-shaped curve. It's because of your electrons. Your electrons come out with a range of energies. Right? It has a range of energies. There's an average K of electrons. Some are very high, some are very low. So when you increase your stopping potential by a little bit, you will cut off a small amount of electrons. Do you agree? So you will have a small drop in the current when you have a increase in potential. When you increase your stopping potential by a bit more, in this range, you will kill off a lot of the electrons. They will not be able to reach the other side of the plate, right? That's why you see a large drop in current for a small change in potential. And there's a very small amount of electrons with a very high Ke, which is why you have a slow decline for the last bit of the ID graph. Okay, so this is actually pretty deep. Right, I'm doing it right on the first part of the lesson. And I didn't include it purposely in the notes because I'm not sure the likelihood of appearance. This notes contains the 90% probability, right? These are the very rare questions. I'm not sure about how it really works, right? So I'm not sure how likely it is, so I didn't put it in case you are overloaded with too much knowledge, right? But for those who are here and in this lecture and reading this video at home, you will see this and understand this, right? So lecture 3, first 10 minutes is something that is not in your notes. You may want to take a look at it. You want to write down, right? Before your exam, if you have already accomplished the whole quantum and you want to learn something extra. Okay? So I'm giving you a range of options. You need to kill yourself, but if you want to learn more, you have. Right, so now let me go back to explaining this, back to the main flow of the lecture. Right, there's constant arrival rate of photons, which means constant rate of electrons. Current is constant. Right? Also, we assume same metal. So for different wavelength of light, the energy of photons will be different. We have different stopping potentials using Einstein's equation. Right? Every time you're talking about stopping potential, you must use Einstein's equation of HF equals to E Vs plus phi. Okay. Next graph. This one also very interesting. So here I want to rotate out, and